Welcome back to Code and Codes. In today's video, we will take a deep dive into the world of unsupervised machine learning, covering some key algorithms and concepts essential for the AI interviews. So, hey everyone, I'm Selma Kandar, and today we are continuing our journey to crack AI interviews with some powerful techniques. If you missed the last video, check the link in the description below. It is packed with the valuable insights you will need. So before going to the actual content, I wanted to show to my new viewers like what and all the sections actually we are going to be prepared for the AI interview. And these sections actually are divided into the 10 different parts from machine learning to the C and basic OS. And currently this video is the part of the machine learning section where we are going to be explore these topics, and into the last videos actually I already explored the some of the topic. Okay. So this is the another step in mastering the AI interview. So be sure to subscribe and hit the notification bell so you don't miss out on upcoming videos in this series. Now let's dive into the today's content. Okay, so I will go to the slide. Okay. Hmm, yeah. So in this video, we are going to be cover the unsupervised machine learning, the K-means clustering algorithm, how we can able to choose the optimal number of the K clusters, and the k-means versus the KNN, which is also called as k-nearest neighbors. Then we will see the principal component analysis and their intuitions, and how to find the optimal PCA components. Okay, so let's start with the first topic, which is the unsupervised machine learning. Okay, so this topic I already covered in my first video. Okay, so if you still didn't watch that video, so please go to the description and check out the link. So here actually I will give the brief of this unsupervised machine learning. So inside the unsupervised machine learning, like first I will select my pen. Okay. So inside the unsupervised machine learning, okay, so whatever the data set it is there, each example, we don't, for each of the example, we don't having any label. Okay. So with the help of that input data set only, whatever our unsupervised machine learning algorithm is there, it will try to find out the insights, okay, with the help of the pattern recognition or the clustering, okay, and also I mean some of the machine learning unsupervised machine learning algorithms are there. It will try to reduce the dimensions of the features, okay. So this is just kind of the brief of the unsupervised machine learning. Okay. So inside the unsupervised machine learning, like there are the various algorithm actually we are going to be explored. Okay. For example, the K-means clustering algorithm. Okay. And also the principal component analysis algorithm is also be there. Okay. So in this video, like we are mainly focusing on this two algorithm because uh, in the interview, like these two algorithm, the most of the interviewers they will ask. Okay, so first let's move to the K-means clustering. Okay, so as the name suggest, the K-means clustering is the unsupervised machine learning algorithm, and whatever the data points are there which we are going to be used inside the K-means clustering, uh, these data points it don't having any label because it is the unsupervised machine learning algorithm. And when we feed this data point to the K-means clustering algorithm, so what actually it will do, it will try to create the coherent clusters of the data points uh, with respect to the number of the K. Okay, means it will create the K coherent cluster. So here actually I am saying why actually I am using the word the coherent cluster, because whatever the cluster which will created by the K-means clustering, it will having the same similar kind of the features actually it will be there. Okay, so because of that it will with the respect to that it will create the K cluster. Okay, so now if you see the inside the K-means clustering, so there are the mainly three steps are there. Okay, so the step one is like, first thing like we need to initialize the clusters, means we need to initialize the k random centroids. Okay, so based on the whatever the k number actually we are choosing, so on the based on that we need to initialize the k random centroid. And after that the second step is like there is the cluster assignment step is there. Okay, cluster assignment step is there. And the after the cluster assignment, the third step is like the centroid moving step is there. Okay, and whatever this step is there, the step 2 and step 3, it will be the repeated step. Okay, until there is the no further movement into the centroid. Okay, so up to that actually this step it will gets repeated. Okay, so how actually this algorithm actually works, so let's will look at the insights. Okay, so as I said, like first we need to choose the number of the k. Okay, so in this case if we choose the number of the k as 3, so on the based on that we need to randomly generate the k centroids. So in this case, because of we chosen the k is equal to 3, so there are the 3 randomly generated centroids actually it will be there. Okay, so this is the centroid 1, this is the centroid 2 and the centroid 3. Okay, then the next step is the cluster assignment step. So in this step what actually it will be happen, like whatever the randomly generated centroid, okay, with respect to that each data point it will find the, means we need to find the Euclidean distance between each data point and that randomly generated centroid. So whatever the closest points are there, okay, that that points actually we need to assign to that particular centroid only. Okay, so for example, if you can in this figure if you can see, like this data point is closest to the this centroid, so because of that it is assigned to this particular centroid region. And whatever these data points are there which is in the green, it is closest to the this randomly generated centroid, so this is because of that it is inside this region. And whatever this blue centroid it is there, it is closest to this all these data points, so because of that it is assigned to the this region. Okay, so after this step is completed, then we need to go to the centroid moving step. Okay, so in that whatever the assigned regions are there, or whatever the assigned data points are there with respect to the each centroid, we need to compute the centroid for that particular data points. Okay, so with that step what will happen, like for this region, okay, for this red region, the initially we having the centroid here. Okay, but after recomputing the centroid, our centroid is moved from this point to the this point. Okay, then after that with respect to this green region, if you can see, like the initially we having the centroid at this point, but after after recomputing the centroid value with respect to these green points, our centroid will move from the this point to the this point. In the same way, for in this blue region also our centroid is initially it was there, but after recomputing of the centroid, then it will move to the this point. Okay, so this kind of the repeated step actually we need to do. Again we need to find out with this respect to the new centroid. Again we need to find out the Euclidean distance between the other data points and with respect to this new centroid. And again it will create the regions, and again we need to do the centroid movement step. Okay, so this until actually when actually we need to do, until there is no further movement into the centroid. So up to that actually these steps it will get repeated, and we will get the final cluster like this. Okay, like this is the cluster 1 and this is the final centroid, this is the cluster 2 and this is the final centroid, and this is the cluster 3 and this is the final centroid. Okay, so accordingly, based on the number of this particular k value, you will get the number of the centroids. Okay, so this is the K-means clustering algorithm. Okay, so I hope you got the point. Okay, so now the question is like how to choose this optimal number of the clusters. Okay, so like there are the various methods are there where we can able to find dynamically, instead of choosing the cluster kind the static way. Okay, we can able to find the number of the cluster dynamically. Okay, so there are the various methods are there. So here actually we will discuss such two methods. So first method, it is called as the elbow method. Okay, so inside the elbow method, what actually it will be there. Okay, so depending on the k values, means first we need to choose the range of the k, like from 1 to, for example, 11. And depending on this range of k, we need to plot the WSS error. Okay, so what is this WSS? So the uh, WSS means within cluster squared sum. Okay, within, here I will write this, within cluster squared sum. Okay, so that thing actually, that error actually we need to find. And with respect to each number of the cluster, for example, first we will go with the number of the cluster 1, and we need to find this WSS error and we need to plot here. Then again we need to move to the we need to keep the number of the cluster 2. Okay, then with this, whatever the cluster is created by, whatever the two cluster will be created by the K-means clustering algorithm, with respect to that, again we need to find out this WSS error. So like that actually we need to do. Okay, so first we will see like how this WSS error actually it will be there. Okay, so here suppose for the number of the cluster 3. Okay, after k-means clustering algorithm, the I will get the clusters like this. Okay, so the WSS error means the within cluster squared error, squared sum. Okay, means whatever with respect to this cluster 1. Okay, we need to again find out the equivalent distance between the centroid and each of the point, and whatever the sum of all this squared distance actually we need to take, and that is the our WSS error for the for this cluster. Okay, then again we need to do some for this cluster, again we need to do for this cluster. Okay, and whatever the sum actually it will be computed, so that actually we need to plot here. Okay, so like that, for each of the number of the cluster, whatever the respected WSS error we need to plot. Okay, and in this plot, like the we need to find out the point where the kind of the elbow shape is making. Okay, so if you can see here, like here you can see this is looking like a kind of the elbow. Okay, so here we can see the we can find out the this n k of 4 is kind of the optimal cluster number of the cluster, optimal number of the cluster. Okay, so like that, this elbow method actually it will be work. Okay, so then another method is there, which is called as the Siloti score. Okay, so inside the Siloti score, how means it will we can able to find. So the Siloti score. Okay, here I will write this. Okay, okay, sorry if I yeah, sorry if my spelling is not correct. Okay, yeah, so the Siloti score will measure like how it will measure like how each data point is similar to the cluster where it is present. Okay, means how that particular data points are the similar to the cluster where it is belongs. Okay, means whatever this data point is there, how much it is similar to the this cluster only. Okay, which it is belongs, and how it is different from the other cluster, means this data point, like how much it is this different from this other cluster. Okay, so whatever that score it is there, it is called as the Siloti score. Okay, so with respect to that, uh, means again we need to choose the range of the k, for example 1 to 10 or 1 to 20, and with respect to that we need to find out the CLOT score for each of the K clusters. Okay. And where we are getting the CLOT score is the highest one. For example, for the number of the cluster 5, actually we are getting the highest CLOT score. So that actually we will consider as the optimal number of the clusters. Okay. So like there are the various other methods are there, but the most popular these two methods are there, where actually we can able to get the optimal number of the clusters. Okay. So I hope you got the idea. Okay. Yeah. So now let's move to the next thing, like K-means versus KNN. Okay. So this is kind of like a very common question asked by asked in the interviews, like what is the difference between the K-means clustering and the K-nearest neighbor. Okay. And this is the most of time it is kind of very confusing. Okay. So the KNN, like it is also called as the K nearest neighbor. Okay. K nearest. Okay. Neighbors. Okay. It is also called as K nearest neighbors. Okay. So the the most kind of the most, I can say, biggest difference between the K means clustering and the K nearest neighbor is K means clustering is the unsupervised machine learning algorithm, but KNN is the supervised machine learning algorithm. Okay. So inside the KNN, like what will be there along with the each example. Okay. Along with each example, we having the respected label. Okay. And this K nearest neighbor algorithm is mostly used in the classification thing. Okay. And this algorithm, like how actually it will work. Okay. So that I will showcase. Okay. So suppose you having the data set. Okay. So suppose here I will plot that particular data set. Yeah. Sorry. Okay. And in this data set, you having some positive points and some negative points. Okay. So that I will also plot. Okay. Means, as I said, the KNN will work in the supervised machine learning algorithm, and inside the supervised machine learning algorithm, for each data point we having the label. Okay. So suppose here we having some positive examples like this. Okay. Okay. And we having some negative examples like this. Okay. Like this, we having some negative example. Okay. So in the KNN, okay, whatever the new data point will be there. Okay. Means suppose in the KNN, suppose this is kind of one new data point is there. Okay. Which is called as the query example. Okay. So whenever this query example will become, where actually we don't know this example is belongs to the either positive class or it is belongs to the either negative class. Okay. So at that time the KNN, like how it will works. Okay. So first thing is like it will find out the Euclidean distance between each of the, means whatever the data points which is present inside that data set, it will find out the Euclidean distance between the query data point. Okay. Whatever this and whatever all the data points which is present here, it will find out the Euclidean distance between that all the data points. Okay. Then after that, depending on the value of K. Okay. So suppose if the value of K is equal to 3. Okay. So then with respect to value of this K, it will find out the what and all the data points, the majority of the, means or the at least the 3 data points which is closest to the this particular query data points, it will find out. Okay. So in this case, if you can see whatever these 3 data points are there. Okay. Suppose whatever these 3 data points are there, it is closest to the this query data points. Okay. Then what it will do, it will see the label of these three data points. Okay, so here the label of these three data points is the positive. Okay, so because of that, this particular query data point, it is classified as the positive class. Okay, so like that, this k nearest neighbor actually it will work. Okay, and this is kind of very common question actually. It is asked into the interview, like tell the difference between the k-means and the kn. So at that time, just we need to keep in mind, like the kn is the supervised ml and the k-means is the unsupervised machine learning algorithm. Okay, so I hope you got the intuition also behind it. Okay. Okay. So now the next unsupervised algorithm we are going to be explore, which is called as the principal component analysis. Okay. So the principal component analysis, this algorithm actually it is used for the dimensionality reduction. Okay. So whenever whatever the high dimensional data is there. Okay. So in order to reduce, in order to, yeah, whatever the high dimensional data, high dimensional features are there, the with the help of the principal component analysis, we can able to transform that particular high dimensional features to the low dimensional features. Okay, so this particular thing actually it will very helpful in order to speed up the learning algorithm. Okay, in order to reduce the computations and all. Okay, so how? So here actually I will take one example. Suppose you having the data points. Okay, and it having the two features of x1 and x2. Okay, so I can say, in order to represent the data point, for example this. Okay, and you having the two dimensions. Okay, the 2D data point. So in order to represent the each of the data point, you need the two numbers. Okay, two numbers you need. Okay, but if you transform these particular data points into the 1D space. Okay, then in order to represent this data point, you need just kind of one line. Okay, means like that actually you can able to represent. Okay, and in order to represent this 1D 1D transform the data points, you need only one number. Okay, so like that, when you reduce the dimension of the features, then as the effect of that, you are reducing the number of the features also, like whatever the representation numbers are there, that also you are reducing. And as the effect of that, you are end up with the less computations and speed up the learning algorithm. Okay, so in that way, like this is kind of very the high level details of the principal component analysis. Okay, so now let's see, like what is the problem formulation inside the PCA. Okay, so in order to make you understand this, I will again take one example. Suppose you having the this kind of the 2D data set. Okay, and okay, and yeah, here I will take like this. Okay, okay, and this, and there are the two features are there because it is the two dimensional data set. So we in order to represent this each of the data point, we need the two numbers. Okay, so in this particular 2D data set, suppose you having the data points like here. Okay, or like here. Okay, some data points are here. Okay, like some data points are here. Okay, so the principal component analysis, what actually it will do, it will try to find out the such plane. Okay, for example, if it is the 2D, then it will try to find out the line. Okay, like this, in such a way that the square error distance between the actual point. Okay, and and whatever means it will try, first it will try to find out this line, and it will project that whatever the actual data point into that particular line. Okay, like this. So this data point is gets projected here, this data point is gets projected here, and this data point is gets projected here in the same way like this. Okay, and the principle of component analysis, what it will do, it will try to find out this plane or this line in such a way that whatever the square error distance between the actual data point and the projected data point is kind of the minimum. Okay, so whatever this squared error between the actual and the projected data point, this is called as the projection error. Okay, so the objective of the principal component analysis, like to find such the direction vectors. Okay, so this whatever this line or the plane will be there, it is nothing but the direction vectors. So it will try to find the such direction vectors which is denoted by the u. Okay, this denoted by the u. Okay, if I say the u1 means vector 1, if I say the u2 means vector 2, like that. Okay, so like that it will try to find out such k vectors. Okay, and on that particular plane means with this vector it will create kind of such line or the plane, and on that particular plane it will project that the actual data points, and in a means whatever this directional vectors are there, it needs to be in a such manner so that whatever this projection error is there, that will be the minimum. Okay, so that is the objective of the PCA. Okay, so when in your data set, okay, if you having the n features, okay, for example in your data set, if you having the n features, okay, and if this particular n features, if you want to reduce to the k features, okay, so at that time you means whatever your PCA will be there, it needs to be create the k directional vectors. Okay, then only we can able to reduce the dimension from n to k. Okay, like this, u1 to uk. Okay, so this is kind of the simple intuition behind the principal component analysis. Okay, so now let's see like what is the algorithm steps for the principal component analysis algorithm. Okay, so the very first step of the principal component analysis is like, first we need to either normalize our features, or we need to take the uh, either we need to do the feature scaling, or we need to take the mean normalization. Okay, because if your features will having a very different scale, okay, then at that time in the PCA actually it is not only it is kind of very expensive with the terms of computationally, but also whatever the projection error is there, it will get the higher. Okay, so first step of the PCA is either scale the features or get the mean normalization. Okay, so first step is like we will do the mean normalize our feature, okay, in the data set. So how it will be mean normalize? Okay, so whatever the xj features are there, okay, so you need to mean normalize that. Okay, so in order to normalize this uh, xj features of your data set, okay, you need to find out first mu j, okay, which is called as the mean at j. Okay, so how actually it will we can able to find out this? The formula is 1 upon m summation of I is equal to 1 to m of x J I. Okay, means the jth feature into the ith example. Okay, so like that, you need to find out the mu, and then after that, this each xji, okay, means each jth feature into the ith example you need to replace with the xj minus mu j. Okay, so that is the first step, like you are doing the mean normalization, means all the features will come into the same scale only. Okay, then after that, the second step is is you need to compute the covariance matrix. Okay, so in order to compute the covariance matrix, the formula is, yeah, so this is the covariance matrix, and it is denoted by this symbol. Okay, and it is computed by the formula 1 upon m, then summation of I is equal to 1 to m, then you need to take the xi, means ith example, and you need to do the matrix multiplication with xi transpose. Okay, so with this operation, actually you will get the covariance matrix. Okay, so once you get the covariance matrix, then you need to find out the eigenvectors for this covariance matrix. Okay, on covariance matrix. Okay, so once you find these eigenvectors, okay, so it will, means you will get the final matrix like this. Okay, okay, where the each column will represent the one directional vector, like u1, okay, then u2, okay, then u3. Okay, like that you will get all the un, means if you having the n feature, you will get the n directional vectors. So here, okay, and the size of this matrix is n by n. Okay, means n by n features are there. Okay, then the fourth step is like, okay, if you want to reduce the dimension of the features from n to k, then from this covariance matrix, from this eigenvectors, you need to select the kth eigenvectors. Okay, for example, the subset of the kth first k column, actually you need to select. Okay, so after selecting this, okay, here I will write, so select the k eigenvector, which is nothing but the k columns from the eigenvector matrix. Okay, then whatever the dimension of this matrix, after selecting the kth eigenvector, it will become n by k. Okay, right? Then after that, what actually we need to do, we need to take the transpose of above matrix. Okay, okay, so after taking the transpose, okay, the dimension of this matrix, means whatever this matrix, it will become the k by n. Okay, means it will become like this. Okay, where we having this u1, okay, then we having the directional vector 2, like that we having the uk vectors. Okay, and it having the dimension k by n. Okay, then after that, the final step is like, okay, whatever this matrix, the transpose matrix is there, we need to multiply this matrix with the actual feature matrix. Okay, H up. Okay. So the feature matrix, it will having the size of n by 1 because each example will having the n features. So it having the size of n by 1, and after multiplying this k by n matrix, if I do the matrix multiplication with n by 1, okay, I will get the k by 1 vector, okay, which is nothing but the means whatever these n features, actually we transform to this k features. Okay, so like that, these are the total 6 steps are there inside the PCA algorithm. Okay, so I will just again briefly tell, like, first we need to take the mean normalization of the features, then we need to compute the covariance matrix, then we need to compute the eigenvectors on the covariance matrix. Then after that, if we want to reduce the dimension from n to k, we need to select the k vectors, k columns from the eigenvectors matrix, and we need to take then after that transpose of that particular matrix, which will make from the n by k to the k by n, and we need to multiply with the original feature matrix, which is having the n by 1 dimension, and after multiplying it by, we will get the k by 1, which is the dimensional reduced matrix actually we will get. Okay, so these are like actually all the steps are there inside the PCA. Okay, so now what it means in these steps, actually what actually we are doing, we are reducing the dimension from the matrix n by k. Okay, but in the same way, we can able to reproject whatever the matrix which is dimensionally reduced from k to n. Okay, means into the PCA, like what actually we will do, we will reduce the dimensions of the features from the n to k. Okay, and inside the reprojection, we can able to again retrieve this particular the original data by again transforming this k matrix, means this k vector to the n. Okay, so how actually we need to do? So here, whatever this matrix is there, which is this one, okay, where actually we are getting this k by n thing. Okay. Yeah, yeah. So not whatever this fourth step matrix is there, is after eigenvectors, whatever the after eigenvectors, whatever the which we selected this matrices like n by k. Okay, so it will looks like this. Okay, which having the okay u1, u2, okay, up to we having the k uk directional vectors actually we having, and the dimension of this matrix is n by k. Okay, and from where actually we will get this matrix, means after applying the eigenvector on the covariance matrix, we will get the n by n, and after selecting this initial k vectors, we will get this n by k matrix. Okay, so what actually we need to do, whatever this n by k matrix is there, again actually if we multiply the uh, if we multiply this k by 1, means whatever the after the PCA whatever the output which we are getting, which having the k by 1, which having the k by 1 dimension. Okay, so if we multiply this with the k by 1 dimensional vector, okay, means this n by k, if we do the matrix multiplication to the k by k and k by 1 matrix, so we will get the again n by 1 matrix. Okay, so this matrix is the approx, means approx of the original n by 1. Okay, and it is denoted as x approx. Okay, because it is not having the exact cat values, but it is the approximate of this original one. Okay, so like that also we can able to reproject also inside the PCA. Okay, so I hope you understand this thing. Okay, so now the next thing, like how to find the optimal number of the principal components. Okay, means whatever the this k things actually we are here the statistically actually we are taking, but how actually we can able to find this component in the optimal way, such that after after like plotting or the transforming all the data points to that particular k vectors, we will get the minimum projection error. Okay, so how to find out this number of the optimal number of the principal component. Okay, so for that there are the various methods are there. Okay, so the most popular method is like, first we need to find out the mean mean square mean projection square error. Okay, first we need to find out the mean projection square error. Okay, here actually I will write that. Okay, and once you find out this mean projection square error, the next step actually we need to find out the we need to find out the variation in the data. Okay, variation in the data. Okay, so first we will see like how to find out this mean projection square error. Okay, so in order to find out this mean square error, means projection square error, the formula is 1 upon m. Okay, summation of I is equal to 1 to m, then the squared Euclidean distance between, okay, squared Euclidean distance between the ith example and their approx of I. Ith example means whatever this reprojection which we are did into the previous slide. Okay, so that actually we need to find with respect to the ith example. Okay, we need to take the squared Euclidean distance of that. Okay, and we will get the final mean projection square error. Okay, then the next thing is like how to find out the variation into the data. So this is the formula is 1 upon m summation of I is equal to 1 to m, and we need to take the squared Euclidean normalization of the xi. Okay, and then after that what actually we need to do, we need to divide these two values. Okay, means whatever this mean square error, okay, mean square, sorry, mean uh, projection square error divided by this variance in data, in data. Okay, and if this particular value, if this value is between the range of 0.015 to 0.01, then we can say that like we having the, means whatever the k, whatever the k directional vectors which we are selected statically, that is the giving the better output, or it will give the minimum projection error. Okay, means it having this particular division, if will come into this range. Okay, so this is the one of the way in order to find out the optimal number of the principal components. Okay, so there are the other ways are there, like by finding out the SPD and all. Okay, but this is kind of more effective or commonly used. Okay, yeah. So I think uh, this yeah, I think I completed for today's session. Okay. So if someone still not subscribed to my channel, please subscribe to it, and please share this video to your friends or someone like preparing for the AI interview and all. Okay. And thank you so much.